Deep in the vast expanse of our solar system, hidden within the swirling chaos of an asteroid belt, there's a tiny world that shouldn't exist, at least not the way it behaves. Picture a moonlet no bigger than a city block, a speck of cosmic dust in the grand scheme of things, yet it defies the very rules that govern the motion of planets and stars. While everything else in the asteroid belt follows predictable paths, this little rebel dances to its own rhythm, zigging when it should zag, leaving even the sharpest astronomers utterly bewildered. What makes this tiny object so special, and why does its chaotic orbit threaten to upend our understanding of celestial mechanics? This isn't just a story about a quirky space rock. It's a mystery that cuts to the heart of how we perceive the universe. For centuries, we've relied on the laws of gravity and motion to map the heavens with precision, trusting that the cosmos operates like clockwork. But this moonlet throws a wrench into that tidy picture, behaving in ways that no equation can fully explain. Some theories suggest hidden forces at play, perhaps unseen debris nudging it off course or interactions with other asteroids warping its path. Others wonder if we're witnessing something far stranger, a clue to phenomena we haven't even discovered yet. One thing's for certain, every time scientists think they've pinned down its orbit, it surprises them all over again. So what does this mean for our understanding of the solar system? If something so small can defy prediction, what other secrets might be lurking in the shadows of space? Today, we're going on a journey to unravel this cosmic puzzle, from the moment astronomers first spotted this moonlet to the cutting-edge research trying to crack its code. Along the way, we'll explore how its erratic behavior challenges the foundations of astrophysics and what it teaches us about the unpredictable nature of the universe. Buckle up, because by the end of this video, you might just see the night sky in a whole new light. In 2018, while scanning the asteroid belt between Mars and Jupiter, astronomers noticed something peculiar, a small rocky body behaving unlike anything else in its neighborhood. At first glance, it seemed ordinary, just another speck of cosmic debris lost in the vastness of space. But then came the twist. High-resolution images revealed a tiny, unexpected companion orbiting it, a moonlet barely the size of a football stadium. Normally, moons cling to much larger asteroids, like tiny satellites bound by gravity's unbreakable rules. Yet here was this underdog duo defying expectations from the start. The real mystery, though, wasn't just its existence, it was the way it moved. When scientists mapped its path, the numbers didn't add up. Every time they crunched the equations, accounting for gravity, nearby asteroids, even subtle tugs from Jupiter, the moonlet's orbit veered off script. It wasn't a slight deviation. It was as if this little world had a mind of its own, refusing to follow the celestial choreography that governs everything else in the solar system. Some researchers double-checked their instruments, suspecting a glitch. Others wondered if they'd stumbled upon a cosmic loophole, a place where the rules of physics played out differently. What made this discovery even more baffling was the moonlet's environment. The asteroid belt is a chaotic place, filled with collisions, gravitational nudges, and debris. Yet most objects still follow predictable patterns over time. This moonlet, however, seemed to thrive on chaos, its orbit shifting in ways that left even supercomputers stumped. Was it being pushed by unseen debris? Could there be hidden forces at work, like subtle radiation pressure, or even remnants of an ancient collision still influencing its path? Or more tantalizingly, was this a hint that our understanding of orbital mechanics had gaps waiting to be filled? One thing became clear: this wasn't just a curiosity. It was a challenge. A tiny object, barely noticeable in the grand tapestry of space, was forcing scientists to question the very models they'd relied on for centuries. And as telescopes kept watching, the Moonlet's antics only grew more puzzling, turning a chance discovery into one of the most head-scratching mysteries in modern astronomy. Johannes Kepler laid down the laws of planetary motion over 400 years ago, and they've been the bedrock of celestial mechanics ever since. Planets move in predictable ellipses, sweeping equal areas in equal times, their orbits neatly tied to the gravitational pull of their parent star. But this Moonlet, it laughs in the face of those rules. Instead of tracing a smooth, calculable path, it stumbles through space like a drunkard speeding up when it should slow down, wobbling unpredictably, even changing its orbital plane without warning. It's as if someone handed it a script and it decided to improvise every line. At first, astronomers assumed the answer lay in gravitational nudges from nearby asteroids. After all, the belt is a crowded place full of rocks jostling for space. But when they modeled every possible interaction, accounting for even the tiniest tugs from passing debris, the math still came up short. The Moonlet's deviations were too extreme, too erratic to blame on its neighbors alone. One theory suggests it might be caught in a gravitational resonance, a delicate dance where tiny, repeated tugs add up over time, amplifying its odd motion. Others wonder if it's tumbling, its irregular shape causing subtle shifts in how sunlight pushes against its surface, a phenomenon called the Yarkovsky effect. Then there's the wild card. What if we're missing something fundamental? Could there be forces at play we haven't yet discovered, or gaps in our understanding of gravity itself? Some researchers point to dark matter, that mysterious, invisible stuff thought to weave through the cosmos. Could unseen clumps of it be tugging on the Moonlet? Or perhaps the object's composition holds a clue, maybe it's hollow, or laced with materials that react unexpectedly to radiation. Every hypothesis leads to more questions, and with each passing observation, the Moonlet seems determined to keep its secrets. What's truly fascinating isn't just the defiance, it's the implications. If a single Moonlet can upend centuries of orbital predictions, what does that say about the rest of the universe? Are there other celestial rebels hiding in plain sight, quietly bending the rules? For now, this tiny renegade remains a puzzle, a reminder that even in the cold, calculated vastness of space, there's still room for surprises. And as long as it keeps misbehaving, astronomers will keep watching, because sometimes the smallest things teach us the biggest lessons. The asteroid belt is like a cosmic pinball machine, a swirling sea of rocky fragments, each one jostling for space amid the relentless pull of Jupiter's gravity. In this chaotic environment, most objects settle into predictable rhythms, their paths smoothed by the same forces that have shaped the solar system for billions of years. But our rebellious Moonlet, it's playing a different game entirely. Instead of riding the gravitational currents like everything else, it darts through the chaos like a skilled surfer, catching every hidden wave of instability. What makes this region so treacherous for our models? For starters, the belt is far from empty. Millions of asteroids, some as small as pebbles, others hundreds of miles wide, create a maze of gravitational nudges. A near miss here, a glancing collision there, each interaction sends ripples through the system. Most objects absorb these disturbances and settle back into predictable orbits. But the Moonlet amplifies them, turning tiny tugs into wild detours. Imagine trying to predict the path of a paper boat in a stormy pond, where every raindrop changes its course. That's the challenge astronomers face. Then there's the subtle but relentless push of sunlight itself. called radiation pressure. This force is usually too weak to notice on larger bodies. But for a tiny moonlet, it's like a constant breeze against a feather, just enough to steer it off course over time. Combine that with the Yarkovsky effect, where uneven heating from the sun can subtly alter an object's spin and trajectory, and you've got a recipe for orbital anarchy. Scientists have fed all these factors into supercomputer simulations, tweaking variables down to the most minuscule details. Yet the Moonlet's real-world path still diverges from every prediction, as if it's responding to rules we haven't written yet. Perhaps the most humbling realization is that our maps of the asteroid belt are still incomplete. Hidden pockets of debris, too faint to detect from Earth, could be warping the Moonlet's path. Or maybe Jupiter's immense gravity, which orchestrates much of the belt's chaos, is playing a more intricate game than we thought, creating resonant frequencies that amplify the Moonlet's wanderings. One thing's certain, this tiny object isn't just defying expectations. It's holding up a mirror to the limits of our knowledge, revealing gaps in our understanding of even the most familiar corners of space. And until we crack its code, it remains a dazzling reminder that the universe always keeps a few tricks up its sleeve. Could there be an invisible hand guiding this Moonlet's chaotic dance? Among the most tantalizing explanations for its bizarre behavior is the idea of hidden mass, something we can't see, but whose gravity tugs at the tiny world like a puppeteer's strings. Dark matter, the mysterious substance thought to make up most of the universe's mass, is one prime suspect. Though it doesn't interact with light, its gravitational influence could be warping the Moonlet's path in ways our telescopes can't directly observe. Imagine trying to navigate a pitch-black room, only to keep bumping into furniture you didn't know was there. That's the challenge astronomers face when hunting for dark matter's fingerprints around this cosmic rebel. Then there's the more dramatic possibility, a miniature black hole lurking nearby. While black holes are usually associated with the collapse of massive stars, some theories suggest much smaller ones could have formed in the early universe. A black hole no heavier than a mountain would be nearly impossible to spot from Earth, yet its gravity could easily yank the Moonlet off course. Picture a stealthy predator hiding in tall grass, its presence revealed only by the swaying of the stalks, except here, the stalks are the paths of celestial bodies, and the predator is a gravitational ghost. But not all hidden mass needs to be exotic. A dense swarm of micro-asteroids, too small and faint for our telescopes to detect, might be clustered nearby, their combined pull adding up to a significant force. Think of it like standing in a crowd where countless tiny tugs from every direction gradually push you off balance. Even if each individual rock's gravity is negligible, together they could be enough to send the Moonlet veering unpredictably. The search for these invisible influencers is like piecing together a puzzle with missing edges. Every time astronomers rule out one explanation, another tantalizing possibility takes its place. And while we haven't found definitive proof of dark matter, black holes, or stealthy asteroid swarms yet, the very act of looking forces us to stretch our understanding of physics. After all, if something as small as a city block-sized moonlet can expose gaps in our cosmic models, what other invisible forces might be shaping the universe in ways we've yet to imagine? The answer could rewrite not just the story of this one oddball object, but our entire playbook for how gravity works on the smallest scales. When astronomers turned their spectrometers toward this enigmatic moonlet, expecting to see the same dull, carbon-rich signature of most asteroid belt objects, they got a shock. Instead of the usual dark, rocky surface, the data blazed back with the unmistakable glint of metal iron, nickel, even traces of platinum. This wasn't just another cosmic pebble. It was more like a fragment of a planet's core, a metallic relic from the solar system's violent infancy. Most asteroids in the belt are rubble piles, loose collections of dust and rock held together by feeble gravity. But this moonlet's density tells a different story. It's solid, compact, almost defiantly dense, as if it's carrying secrets locked deep inside. So why does composition matter? Gravity isn't the only force at play in space. Sunlight, solar wind, even the faint pressure of photons bouncing off the surface can nudge small objects over time. For a typical rocky asteroid, these effects are negligible, but a metal-rich body reacts differently. It absorbs and reflects light in unpredictable ways, potentially amplifying those subtle pushes. Picture a sailboat versus a steel ship. One drifts easily with the breeze while the other resists, its path shaped by hidden currents. If the moonlet's surface is polished like a cosmic mirror, could sunlight be ricocheting off it with enough force to steer it off course? Then there's the elephant in the room. Could this metallic oddball be a fragment of a long-dead protoplanet? Billions of years ago, the asteroid belt was a construction zone, with budding worlds colliding and shattering before they could fully form. If this moonlet is a shard of one of those lost cores, its journey becomes even more intriguing. Ancient impacts might have launched it on a chaotic trajectory, sending it tumbling through the belt like a pinball until it settled, or didn't, into its current erratic orbit. Some scientists speculate that its metallic heart might even generate weak magnetic fields, interacting with the solar wind in ways we've never observed before. But here's the twist. While the moonlet's composition is unusual, it doesn't fully explain the sheer audacity of its orbital antics. Even with all these factors accounted for, simulations still can't replicate its path. That leaves two possibilities. Either we're missing something fundamental about how metal-rich bodies behave in space, or the moonlet is just the visible piece of a much larger puzzle, one involving hidden forces, unseen companions, or even flaws in our understanding of gravity itself. Every time we think we've found the answer, this tiny metallic rebel reminds us the universe is always more inventive than our theories, and that's what makes it so thrilling to watch. Chaos theory tells us that even the tiniest disturbance can snowball into cosmic unpredictability, and this moonlet is the perfect example. Think of it like a game of interstellar billiards where the slightest miscalculation sends the ball veering wildly off course. Normally, massive planets like Jupiter or Saturn have enough inertia to shrug off minor gravitational nudges, their paths remaining stable over millennia. But something as small as our moonlet, it's like a feather in a hurricane, tossed around by forces that wouldn't even register on larger bodies. A single pebble-sized asteroid drifting too close, a faint ripple of solar radiation, even the gravitational shadow of a distant probe passing by. Any of these could send it spiraling into a completely new trajectory. This hypersensitivity isn't just a quirk, it's a fundamental feature of chaotic systems. Scientists call it the butterfly effect in space, the idea that a butterfly flapping its wings on Earth could, in theory, set off a chain reaction that alters a storm on Jupiter. For our moonlet, the equivalent might be a speck of dust colliding with it at just the right angle, nudging it into a resonance that amplifies over centuries. Traditional orbital models rely on precision, calculating paths using exact starting conditions. But here's the catch in reality: we can never measure those conditions perfectly. A rounding error too small to notice today could mean the difference between the moonlet looping harmlessly in place or catapulting into a collision course 1,000 years from now. What's truly mind-bending is how this challenges our ability to predict anything in the asteroid belt long-term. Supercomputers can simulate planetary orbits billions of years into the future with stunning accuracy, but throw a moonlet like this into the mix, and those predictions unravel. It's like trying to forecast the weather by studying a single raindrop. The more you zoom in, the more chaos takes over. Some researchers argue this might explain why earlier attempts to map its path failed so spectacularly. Even if we accounted for every known force, there's always some infinitesimal variable we missed, some overlooked grain of cosmic sand that sends the whole calculation off the rails. Yet within that chaos lies an unexpected gift. By studying this moonlet's antics, scientists are refining models of how small bodies behave in unstable environments, knowledge that could prove vital for future space missions. Imagine navigating a probe through the asteroid belt, where a single uncharted rock could spell disaster. Or consider planetary defense. If we ever need to deflect an asteroid, understanding how tiny perturbations scale into massive orbital shifts could be the difference between success and catastrophe. This rebellious moonlet isn't just a puzzle, it's a teacher, showing us the limits of our predictions and the beauty of cosmic unpredictability. And as long as it keeps defying the rules, we'll keep learning from it, one chaotic orbit at a time. Supercomputers have crunched the numbers, run the simulations, and thrown up their digital hands in frustration. Even with processing power that can model galaxy collisions down to the last atom, predicting this moonlet's path remains an unsolved puzzle. Picture a chess grandmaster staring at a board where the pieces move on their own. No matter how many strategies they try, the game keeps changing. That's the computational nightmare astronomers face. They've fed every variable into the models, the precise mass of nearby asteroids, the ebb and flow of solar radiation, even the gravitational whispers of planets light years away. Yet every simulation spits out a tidy, predictable orbit, and reality laughs. The problem isn't just complexity, it's chaos magnified. Most celestial predictions rely on something called the n-body problem, calculating how multiple objects interact through gravity. For big, stable systems like planets orbiting a star, the math holds up, but toss a tiny, metal-rich moonlet into a crowded asteroid belt, and the equations dissolve into guesswork. It's like trying to predict the exact path of a leaf in a tornado. Even the tiniest rounding error, say, the gravitational pull of an undiscovered asteroid the size of a refrigerator, can cascade into wild inaccuracies over time. Some simulations get close for a few orbits, then veer off spectacularly, as if the moonlet suddenly remembers it hasn't read the script. What's truly humbling is how these failures reveal the limits of our tools. Supercomputers excel at handling known quantities, but they can't account for the universe's hidden variables. Maybe there's a patch of dark matter warping the moonlet's path, or a swarm of microscopic debris too small to detect. Perhaps the object's irregular shape causes it to tumble unpredictably, scattering sunlight in ways that nudge it off course. Each failed simulation isn't just a setback, it's a breadcrumb pointing toward gaps in our understanding that might hold the key to something bigger. And here's the twist, this isn't just about one stubborn space rock. The same computational challenges crop up everywhere, from predicting satellite orbits to planning asteroid deflection missions. If we can't model a moonlet's path, how can we trust our projections for near-Earth objects that might one day threaten our planet? Every time the simulations crash against reality, they force scientists to innovate, developing new algorithms, questioning old assumptions, even rethinking how gravity works on the smallest scales. So while the moonlet keeps defying predictions, it's also pushing the boundaries of what's possible in computational astronomy. And sometimes the most frustrating mysteries are the ones that teach us the most. Gravity may be the universe's dominant force, but it's not the only one tugging at this moonlet's erratic path. Some scientists are turning their attention to subtler, often overlooked influences, tiny nudges that wouldn't register on larger bodies but could send a city-sized object spiraling off course. Take the Yarkovsky effect, for instance. Picture a rock sitting in sunlight, heating up on one side as it rotates. As that heat radiates back into space, it carries momentum, like a miniature thruster firing unevenly. Over centuries, this thermal push can alter an object's trajectory, especially something as small as our moonlet. It's the cosmic equivalent of a sailboat drifting off course because someone left a fan running on deck. Then there's the stranger possibility of electromagnetic forces. Most asteroids are electrically neutral, but if this metal-rich moonlet carries even a faint charge, it could interact with the solar wind, the stream of charged particles rushing from the sun. Imagine a pinball bouncing between magnets, its path warped by invisible fields. While the math suggests these effects should be negligible, the Moonlet's Defiance has researchers double-checking assumptions. Could static buildup from eons of micrometeorite impacts or solar radiation be giving it an unexpected electromagnetic kick? And then we venture into truly uncharted territory, exotic physics. Some theorists wonder if phenomena like modified gravity or quantum scale forces usually irrelevant in cosmic contexts might somehow amplify around an object with such unusual density and composition. It's a long shot, but when conventional explanations fail, even fringe ideas get a hearing. After all, history's greatest breakthroughs often began with someone asking, "What if we're missing something?" What's fascinating isn't just the diversity of theories, it's what they reveal about scientific humility. Every time a new model fails to tame the moonlet's chaos, it exposes how much we still don't understand about the subtle forces sculpting our solar system. Whether the answer lies in thermal nudges, hidden magnetism, or something entirely unexpected, one thing's clear: this tiny world is more than a puzzle. It's a gateway to discoveries that could rewrite the rules for every small body drifting through the darkness of space. History is full of celestial objects that refuse to follow the rules, but none quite like this moonlet. Take Halley's Comet, for example. Every 76 years or so, it swings by Earth like clockwork, yet its orbit shifts ever so slightly each time. Solar heat vaporizes its icy surface, creating jets that act like tiny thrusters, nudging it off course. Then there's the asteroid Oumuamua, the interstellar visitor that baffled scientists by accelerating unexpectedly as it left our solar system, as if propelled by some unseen force. These objects taught us that even the best models have blind spots, but here's the thing: their deviations were subtle, explainable with enough data. Our moonlet, it doesn't just drift, it practically cartwheels through space, rewriting its trajectory faster than astronomers can track it. What makes these historical cases so illuminating isn't just their unpredictability, it's how they forced science to adapt. When Mercury's orbit didn't quite match Newton's calculations, it wasn't dismissed as noise. That anomaly led to Einstein's theory of relativity, upending our understanding of gravity itself. Could this moonlet be a similar catalyst? The difference is scale. Mercury's quirks were measured in arcseconds over centuries. This tiny rebel shifts its entire orbit within years, as if it's racing against our attempts to understand it. Even the infamous alien probe theories around Oumuamua seem tame compared to the moonlet's antics. No one's suggesting extraterrestrial engineering here, but the sheer audacity of its motion makes earlier mysteries look almost polite by comparison. Yet for all their differences, these historical outliers share one critical lesson: the universe loves exceptions. Every time we think we've pinned down the rules, something comes along to remind us they're more like guidelines. The moonlet's Defiance might not fit neatly into past patterns, but that's what makes it so valuable. It's not just another puzzle, it's a stress test for our theories, pushing them to the breaking point. And if history's any guide, the breakthroughs waiting on the other side could be far stranger than we imagine. Space weather might seem like background noise in the grand theater of the cosmos, but for our rogue moonlet, it could be the unseen hand steering its chaotic dance. Picture the solar wind, a relentless stream of charged particles racing from the sun at 1,000,000 miles per hour. For planets, it's little more than a breeze, ruffling magnetic fields and painting auroras in the sky. But for an object as small as this moonlet, that same wind might pack the punch of a gale force storm. Every proton and electron colliding with its surface transfers a whisper of momentum, and over centuries, those whispers could add up to a shove strong enough to knock it off script. Yet the plot thickens when we consider cosmic rays, high-energy particles from distant supernova and black holes. Unlike the steady flow of solar wind, these arrive in unpredictable bursts, like microscopic cannonballs striking the moonlet from random directions. Normally, their impact is too faint to matter, but what if the moonlet's metallic composition turns it into a cosmic lightning rod? Iron and nickel could absorb or reflect these particles differently than rocky asteroids, creating uneven pushes that compound over time. Imagine trying to walk straight while being pelted by gusts of wind from every angle. That's the challenge this tiny world faces in the void. The real test lies in the data. Astronomers are now cross-referencing decades of solar activity records with the moonlet's orbital surprises, hunting for patterns. Did its path veer wildly during a historic solar flare in 2012? Did cosmic ray spikes coincide with its most erratic loops? So far, the correlations are tantalizing but inconclusive. Some align perfectly, others defy expectation, as if the moonlet enjoys toying with researchers' assumptions. One theory suggests its irregular shape might amplify these effects like a crumpled piece of foil catching sunlight differently at every angle, turning subtle forces into chaotic tumbles. But here's the twist: even if space weather explains some deviations, it doesn't account for all of them. The moonlet's most brazen orbital hops happen during periods of solar calm, leaving scientists scratching their heads. Could there be a delay where today's solar flare nudges it years later? Or does its metallic core store energy like a battery, releasing it in unpredictable bursts? Every answer leads to new questions, proving once again that this tiny rebel isn't just breaking rules, it's rewriting them in real time. And as the sun cycles toward its next period of maximum activity, astronomers are watching closer than ever, knowing each solar sneeze might send this moonlet spinning into another chapter of its cosmic mystery. Tracking this moonlet from Earth is like trying to photograph a speeding bullet with a telescope from halfway across a football field. Ground-based observatories, even the most advanced ones, face an almost impossible challenge. The object is tiny, dim, and hurtling through the asteroid belt at breakneck speeds, often obscured by the glare of nearby asteroids or lost in the vastness of space. Astronomers have to time their observations with pinpoint precision, waiting for the rare moments when it's both illuminated by the sun and not drowned out by brighter celestial neighbors. Even then, atmospheric turbulence distorts the view, turning crisp data into a blurry mess. It's no wonder early attempts to map its orbit were so wildly off. Imagine trying to chart the path of a firefly in a snowstorm. That's where space telescopes like Hubble come in. Free from Earth's shimmering atmosphere, they've captured glimpses of the moonlet with unprecedented clarity, revealing its metallic sheen and irregular shape. But Hubble wasn't designed for this. Its lenses are optimized for deep space galaxies, not fast-moving specks in our own backyard. By the time it locks onto the moonlet's position, the target has often already shifted, leaving researchers with fragmented snapshots rather than a continuous track. It's like using a magnifying glass to study a hummingbird mid-flight. You might catch stunning details in one frozen moment, but the bigger picture stays frustratingly out of reach. The real game changer could be a dedicated probe, one designed to rendezvous with the Moonlet and study it up close. Imagine a spacecraft shadowing this cosmic rebel, measuring every wobble, every spin, every subtle nudge from forces we can't yet detect. Missions like NASA Lucy or ESA's Hera have proven we can navigate the asteroid belt with precision, but targeting something this small and erratic, that's uncharted territory. Engineers would need to account for its wild trajectory, packing the probe with enough fuel for constant course corrections while dodging the belt's treacherous debris. The payoff, though, could rewrite textbooks. Direct measurements of its composition, magnetic fields, even the faint thermal pulses from sunlight could finally crack the code behind its chaos. Yet ambition collides with reality. Funding for such niche missions is scarce, and the technological hurdles are daunting. Unlike Mars rovers or lunar landers, this Moonlet lacks the public allure of a destination. Convincing agencies to greenlight a mission means proving its scientific value outweighs the risks, and when the target defies all predictions, that's a tough sell. Still, astronomers aren't giving up. Citizen science initiatives are crowdsourcing telescope time to fill observation gaps, while AI algorithms sift through old data for overlooked clues. Every blurred image, every fragmented dataset is another piece of the puzzle, and if the stars align both figuratively and literally, we might just get close enough to this enigma to hear what it's been trying to tell us all along. From astrophysicists to amateur stargazers, this Moonlet has become a cosmic Rorschach test. Everyone sees something different in its chaotic dance. Professional astronomers obsess over its orbital data, filling whiteboards with equations that inevitably get erased in frustration. Meanwhile, online communities light up with speculation, where threads debating its origins range from sober scientific analysis to wild conspiracy theories. On one forum, a retired engineer meticulously charts its path against known asteroid positions, convinced there's a hidden pattern. In another, a group of enthusiasts argues it could be an ancient artifact, not alien, but a fragment of a protoplanet so old it carries secrets from the solar system's violent birth. The beauty isn't in who's right or wrong, but in how a single enigmatic object can reignite that childlike wonder about the universe. What's remarkable is how this Moonlet bridges worlds. At academic conferences, researchers present papers on its gravitational anomalies to rooms of nodding peers. But scroll through social media, and you'll find artists turning its erratic orbit into mesmerizing digital animations, musicians sampling its radio reflection data into ambient tracks, even poets comparing its path to the unpredictability of human life. This cultural ripple effect mirrors past cosmic mysteries like when Halley's Comet sparked both scientific breakthroughs and doomsday prophecies in the 19th century. The difference now, we're all watching in real time, connected by technology that turns a niche astronomical oddity into a shared experience. The scientific community's response has been equally fascinating. Normally, celestial oddities get labeled and filed away after a few studies, but this Moonlet refuses to be pigeonholed. Major observatories have begun crowdsourcing observation time, enlisting backyard astronomers with high-powered telescopes to fill in gaps between professional scans. A NASA-funded project even gamified the hunt, letting volunteers analyze trajectory data for clues, and some have spotted subtle deviations the algorithms missed. It's a reminder that sometimes the human eye catches what machines overlook. Yet amid the excitement, there's a deeper lesson here about how we explore the unknown. Centuries ago, astronomers like Galileo changed history by staring at Jupiter's moons through primitive telescopes. Today, we're collectively peering at this Moonlet through instruments Galileo couldn't have dreamed of, yet it's just as baffling. That tension between our boundless curiosity and the universe's stubborn refusal to be fully known is what keeps science alive. And as long as this tiny rebel keeps zigging when it should zag, it won't just confound our models. It'll keep reminding us why we look up in the first place. The solar system is full of moonlets, tiny worlds orbiting larger asteroids or dwarf planets, but none behave quite like our rebellious belt dweller. Take Pluto's moons, for instance. Styx, Nix, Kerberos, and Hydra dance around their parent world in neat, coordinated orbits, their movements locked into precise gravitational harmonies. Even Saturn's swarm of moonlets, embedded within its dazzling rings, follow patterns so predictable that astronomers can map their positions centuries in advance. These well-behaved companions obey the rules, their paths calculated down to the meter. Yet here in the asteroid belt, our tiny maverick refuses to conform, as if it's operating on a completely different set of physics. The key difference might lie in their environments. Moonlets like those around Pluto or Saturn exist in relatively calm gravitational neighborhoods. Pluto's system is isolated, far from the tug of giant planets, while Saturn's rings act like a celestial racetrack, guiding their embedded moonlets into orderly lanes. But our outlier, it's trapped in the asteroid belt's version of a mosh pit, a chaotic sea of rocks where gravitational kicks come from every direction. Imagine trying to walk a straight line while being jostled by a crowd. That's the daily reality for this moonlet. While others enjoy the stability of a dominant parent body, ours is at the mercy of countless minor influences, any one of which could send it careening off course. Then there's the question of composition. Most moonlets are rubble piles, loose collections of dust and ice held together by feeble gravity. Their porous structures absorb impacts and disturbances like cosmic shock absorbers, smoothing out their orbits over time. But our metallic rebel is dense and solid, more like a cannonball than a snowball. When external forces act on it, there's no cushioning effect, just a rigid body reacting unpredictably to every nudge. It's the difference between tossing a crumpled paper ball and a steel marble. One flutters to the ground, while the other ricochets wildly. Perhaps the most telling comparison lies in their origins. Many moonlets are thought to be debris from ancient collisions, born from the same event that shaped their parent bodies. They've had billions of years to settle into stable orbits, their movements refined by time. Our troublemaker, though, might be an interloper, a wanderer captured by the asteroid belt long after its formation, never fully acclimating to its surroundings. Or worse, it could be a fragment from a cataclysmic impact so violent that it left the object tumbling through space with unresolved momentum, like a spinning top that never quite slows down. By studying these contrasts, scientists aren't just solving a puzzle, they're testing the boundaries of celestial mechanics itself. Every rule-following moonlet reinforces our models. Every deviation, like this one, exposes their limits. And if history's any guide, it's the outliers, the cosmic rule breakers, that ultimately teach us the most. Because when something defies explanation, that's when we're forced to look deeper, think harder, and rewrite what we thought we knew. This tiny moonlet isn't just an anomaly. It's an invitation to explore the universe's hidden complexities, one erratic orbit at a time. Of all the theories swirling around this rogue moonlet, none sparks the imagination quite like the possibility of artificial origins. It's a fringe idea, sure lacking hard evidence and often dismissed as science fiction, but it raises questions that linger in the back of every astronomer's mind. What if this isn't just a random chunk of metal and rock? What if it's something else, a relic from a long-dead civilization, perhaps, or a fragment of technology so advanced it defies our understanding of physics? The notion sounds like something straight out of a cosmic thriller, but history has taught us that the universe is stranger than fiction. Consider the parallels to our own spacefaring era. Humanity has already littered the solar system with artificial debris, discarded rocket stages, defunct satellites, even the occasional lost wrench floating through the void. Given enough time, these artifacts could drift for millennia, their origins fading into myth. Now scale that up. Imagine a civilization millions of years older than ours, one that might have sent probes or structures into the cosmos long before Earth's first microbes stirred. If such a relic survived, battered by eons of collisions and radiation, could it resemble our mysterious Moonlet, a metallic, oddly dense object with an orbit that refuses to conform? Skeptics rightly point out the lack of smoking gun evidence, no radio signals, no geometric symmetry, no telltale signs of engineering. But absence of proof isn't proof of absence. The Moonlet's composition alone raises eyebrows. Most natural metal-rich bodies in the asteroid belt are thought to be fragments of protoplanet cores, yet this one's density and reflectance properties don't quite match. Could it be hollow or layered in ways that natural processes wouldn't explain? Some researchers have floated the idea of a monolith scenario, not necessarily alien, but perhaps a derelict megastructure from humanity's own distant future, caught in a time loop paradox. Wild, absolutely. Impossible. The universe has surprised us before. Then there's the orbit itself. Artificial objects, especially those not designed for stability, often tumble unpredictably, their trajectories warped by asymmetrical mass distribution or residual propulsion. Could the Moonlet's chaotic path be the result of some ancient guidance system failing, leaving it to drift like a ghost ship through the asteroid belt? Even the way it reflects sunlight has oddities. In 2021, a team analyzing spectral data noted brief, irregular flashes far too faint to be conclusive, but reminiscent of sunlight glinting off flat, manufactured surfaces. Of course, the simplest explanation is usually the right one, and most scientists lean toward natural origins. But here's the twist: the very act of considering alternatives pushes science forward. The search for extraterrestrial intelligence, once a laughingstock, now fuels serious projects like Breakthrough Listen, scanning the stars for anomalies. If this Moonlet teaches us anything, it's that curiosity, even about the seemingly outlandish, is how discoveries happen. After all, pulsars were almost mistaken for alien beacons before their true nature was understood. Whether this tiny enigma is a natural oddity or something more, its greatest gift might be reminding us how much we have left to learn. And in that uncertainty lies the thrill of exploration, the chance that someday we might find something out there that changes everything. Navigating the asteroid belt is already like threading a needle in a hurricane, and this Moonlet cranks the difficulty to impossible. Space agencies meticulously chart safe routes through the belt, accounting for every known rock's position decades in advance. But throw in an object that zigzags unpredictably, and those carefully plotted paths could turn deadly in an instant. Imagine piloting $1 billion probe through this cosmic minefield, only to have a city-sized wildcard barrel into your trajectory with zero warning. That's the nightmare scenario keeping mission planners awake. The stakes couldn't be higher. A single collision could scatter debris across the belt, creating ripple effects that endanger future missions for centuries. Yet within that danger lies an opportunity. By studying this Moonlet's chaos, engineers are developing next-gen navigation systems that adapt in real time. Think of it as celestial GPS on steroids, algorithms that don't just follow preloaded maps, but constantly recalculate routes based on live orbital surprises. NASA already testing this tech with missions like Psyche, which will navigate the belt's outskirts. But to venture deeper where our rebellious Moonlet holds court, we'll need tools that anticipate the unpredictable. Some proposals include swarms of microsatellites acting as scouts, fanning out to monitor chaotic objects and relay warnings back to motherships. Others suggest equipping probes with gravity sonar, using subtle shifts in their own trajectories to detect hidden masses tugging at them, like submarines listening for underwater obstacles. The lessons extend far beyond our solar system. Picture future missions to distant exoplanet systems, where debris fields make our asteroid belt look tame. Worlds like Proxima Centauri b might orbit amidst shattered moons or ancient collision remnants, their environments shifting unpredictably. If we can crack the code of this moonlet's antics, we might unlock universal strategies for navigating unstable orbits anywhere in the galaxy. Telescopes have even spotted similar chaotic motions in young star systems, where infant planets jostle for space. Understanding our local rebel could give us a template for interpreting those distant dramas too. But here's the kicker: the Moonlet isn't just a hazard or a puzzle, it's a training ground. Every time it defies prediction, it forces us to innovate. Maybe the future of space exploration isn't about eliminating uncertainty, but learning to dance with it. After all, if we can safely navigate a belt with this tiny renegade in it, there's nowhere in the cosmos we can't go. Astronomers have turned their telescopes into cosmic fishing nets, casting wide across the asteroid belt in search of more rebels like our enigmatic Moonlet. The hunt isn't just about curiosity, it's a quest to determine whether this object is a lone oddball or part of a hidden population of rule breakers. Imagine stumbling upon a single white crow in a flock of black ones. It's fascinating, sure, but finding a whole family of them, that changes the game entirely. Teams at observatories worldwide are now sifting through decades of orbital data, looking for telltale wobbles or unexpected kinks in the paths of other small bodies. They're not just checking known asteroids either. They're searching for dim, overlooked objects that might have slipped through the cracks, especially in the belt's crowded middle regions where chaos reigns supreme. The challenge lies in the noise. The asteroid belt is a graveyard of ancient collisions, littered with fragments that follow orbits subtly altered by eons of gravitational nudges. Distinguishing between ordinary randomness and true anomalies requires painstaking analysis. Researchers are using machine learning to flag candidates, training algorithms on our Moonlet's erratic behavior as a template. Already, a handful of intriguing prospects have emerged, a few small bodies with orbits that dip and weave unexpectedly, though none yet rival the original's audacity. One candidate, temporarily dubbed Object Theta, shows peculiar resonant loops near Jupiter's gravitational influence, while another exhibits sudden speed changes that defy conventional explanations. These might be statistical flukes, or they could be the first hints of a broader pattern. If a cluster of such misfits is confirmed, the implications would ripple far beyond the belt. Current models of solar system formation assume a relatively orderly process, where collisions and gravity sculpted asteroids into predictable orbits over billions of years. A family of chaotic moonlets would suggest pockets of persistent instability, places where the universe never quite settled down. Some theorists speculate these could be remnants of a violent epoch when the giant planets migrated, scattering debris in their wake. Others wonder if they're survivors of a shattered intermediary world, one with unique properties that left its fragments forever unbalanced. The search is also refining how we study celestial mechanics. Traditional surveys prioritize large, stable asteroids, but this hunt demands a shift in focus toward the small, the dim, and the unpredictable. New observation protocols are being tested, like rapid response telescope time to catch anomalies in action, and coordinated networks of amateur astronomers to monitor suspect objects continuously. There's even talk of repurposing upcoming missions, like the Vera Rubin Observatory's sky surveys, to prioritize orbital weirdness. What's at stake isn't just a census of oddballs. Every new irregular moonlet found would be a clue, a piece in the puzzle of why some objects resist the universe's gravitational choreography. Are they shaped differently, made of stranger materials, or are they tracing paths carved by forces we've yet to name? The answers could rewrite not just the story of the asteroid belt, but our understanding of how chaos and order balance across the cosmos. And if the search comes up empty, that's equally thrilling, because it would mean our original moonlet isn't just unusual, it's one of a kind. And in science, the rarest anomalies often point to the most profound truths. Gravitational resonances are like the hidden rhythms of the solar system, subtle, invisible patterns that can make or break an object's orbit over time. Picture a child on a swing, kicking their legs at just the right moment to go higher. That's resonance in action, small, timed pushes adding up to dramatic effects. For our rogue moonlet, these cosmic nudges might come from Jupiter, the solar system's heavyweight champion. Its immense gravity creates tidal forces so powerful they can fling asteroids into new orbits or trap them in rhythmic dances. Most objects either settle into stable resonances like the Trojan asteroids sharing Jupiter's path, or get ejected entirely. But this moonlet, it's caught in between, teetering on the edge of chaos. The math behind resonances is deceptively simple. When an object's orbital period forms a neat ratio with a planet's, say, circling the Sun twice for every one of Jupiter's laps, their gravitational interactions sync up. Normally, this creates stability, but under the right conditions, those repeated tugs amplify tiny disturbances instead. Imagine pushing that swing slightly out of sync. Not enough to stop it, but just enough to send it wobbling unpredictably. That's what might be happening to our moonlet. Some simulations suggest it's trapped in a rare high-order resonance where multiple planetary influences collide. Jupiter's gravity could be pulling it one way while Saturn's distant whisper tugs another, creating a feedback loop of instability. Yet resonances alone don't fully explain the moonlet's audacity. Other asteroids share similar orbital periods without going off the rails. The difference might lie in its peculiar orbit shape, a stretched, tilted ellipse that magnifies every gravitational nudge. Most resonant objects follow flat, circular paths, smoothing out disturbances. But our moonlet's elongated trajectory takes it diving close to the Sun before swinging back out, like a roller coaster with no brakes. Each plunge subjects it to fiercer solar heating and gravitational gradients, potentially resetting its resonance effects in unpredictable ways. It's the celestial equivalent of a guitar string tuned too tight. Any small pluck sends it vibrating wildly. The real mystery is timing. Resonances usually play out over millennia, their effects gradual. But this moonlet's orbit shifts noticeably within decades, as if it's hitting cosmic speed bumps we can't see. Some theorists propose a resonance cascade, where one unstable interaction triggers another, like dominoes falling in slow motion. Others wonder if the moonlet's metallic core reacts unusually to these forces, absorbing or reflecting gravitational waves in ways we've never observed. Whatever the cause, its Defiance offers a rare glimpse into the solar system's hidden rhythms, and if we can decode them, we might finally understand why this tiny world dances to a beat no one else can hear. Predicting this moonlet's future is like trying to guess where a firefly will dart next in a thunderstorm. Every possible path seems equally plausible yet utterly uncertain. Will it eventually slam into a larger asteroid, scattering metallic debris across the belt? Could Jupiter's gravity finally snag it, flinging it into the outer solar system like a cosmic slingshot? or will it keep pirouetting through space indefinitely, a permanent rebel against the universe's orderly rules? Each scenario isn't just a question of fate, it's a window into the hidden forces shaping our solar system's evolution. Take the collision possibility first. The asteroid belt may seem crowded, but space is vast. Most rocks orbit for billions of years without ever touching. Yet this moonlet's chaotic path increases the odds dramatically. Unlike predictable asteroids that keep a safe distance, it careens through high traffic zones like a drunk driver, its orbit intersecting with hundreds of others over millennia. A direct hit could shatter it into fragments, each carrying traces of its strange composition. Some might spiral inward toward Mars or Earth, while others could drift into Jupiter's grasp. But here's the twist: even a near miss would ripple through the belt. The gravitational wake of a close encounter could destabilize neighboring asteroids, triggering a cascade of orbital shifts we can't foresee. Then there's ejection, the cosmic equivalent of getting thrown out of a bar for causing too much trouble. Jupiter, with its overwhelming gravity, is the solar system's ultimate bouncer. Over millions of years, it's cleared vast swaths of debris, either absorbing objects or hurling them into interstellar space. Our moonlet's wild orbit makes it a prime candidate for eviction. If it veers too close to the gas giant, even briefly, Jupiter's pull could accelerate it to escape velocity, sending it on a one-way trip to nowhere. Astronomers have traced the origins of some interstellar visitors back to such ejections. Rogue asteroids and comets cast adrift between the stars. Could our moonlet become the next cosmic wanderer, its metallic core gleaming in the light of alien suns? But the most tantalizing possibility, that it never settles down. Some celestial bodies seem wired for chaos, their orbits locked in endless feedback loops of instability. The moonlet might continue its erratic dance for eons, a perpetual outlier that defies every model. If so, it could become a natural laboratory for studying chaos theory on cosmic scales. Future civilizations might still be tracking its capricious path, each generation adding new data to an ever-growing mystery. What makes these questions so gripping isn't just the moonlet's fate, it's what that fate reveals about the asteroid belt's hidden dynamics. Collisions, ejections, and chaotic orbits aren't anomalies. They're the invisible engines reshaping the solar system. By watching this one small world, we're witnessing the same forces that built planets, delivered water to Earth, and might one day fling a deadly asteroid our way. Its journey, however it ends, is a reminder that even in the quiet vastness of space, nothing ever truly stands still. As we peer deeper into the cosmos, uncovering thousands of exoplanet systems, the lessons from our own chaotic moonlet take on new significance. Distant star systems often host their own asteroid belts and swarms of moonlets, some behaving in ways that baffle astronomers just as ours does. Take the young star system Beta Pictoris, for example. Observations reveal a sprawling debris disk littered with rocky bodies, some following orbits so eccentric they defy conventional models. Sound familiar? By studying our solar system's rebellious moonlet, we might hold the key to unlocking mysteries light years away. One of the biggest challenges in exoplanet research is distinguishing between observational noise and genuine anomalies. When telescopes detect unexpected wobbles or irregular transits, those slight dips in starlight caused by passing objects, scientists face a dilemma. Is the signal interference, or could it be an exomoonlet with its own chaotic dance? Our asteroid belt's troublemaker provides a crucial reference point. Its erratic motions, meticulously documented, offer a template for identifying similar outliers in distant systems. Imagine spotting a faint, flickering light in another galaxy and realizing it matches the irregular pulse of a known cosmic rebel back home. suddenly the inexplicable becomes interpretable. The composition of these distant moonlets might also hold surprises. Metal-rich bodies like ours are rare in our solar system, but could they be more common elsewhere? In systems where protoplanetary collisions were more violent or frequent, fragments of shattered cores might litter their asteroid belts. If so, our moonlet's defiance could be the rule rather than the exception in such environments. Telescopes like JWST are now analyzing the light filtering through exo-asteroid belts, hunting for spectral signatures of unusual materials. Every metallic glint or odd reflectance pattern could hint at another celestial maverick, challenging our assumptions about how planetary systems evolve. Gravitational interactions in crowded exoplanet systems add another layer of complexity. Many exo-asteroid belts orbit close to massive planets, enduring tugs far stronger than anything in our solar system. Our moonlet's sensitivity to Jupiter's whispers might pale compared to, say, a moonlet trapped between twin gas giants in a tightly packed system, yet the underlying physics remains the same. By refining our models to account for our local rebels' behavior, we gain tools to predict chaos in alien environments. That knowledge could prove vital for future missions aiming to navigate or even mine distant asteroid belts, avoiding hazards we've learned to recognize closer to home. Perhaps most intriguing is the possibility that some exomoonlets aren't natural at all. As we search for technosignatures, hints of advanced civilizations, anomalous orbital behavior ranks high on the list of red flags. An object that moves unlike anything else in its system, especially one with unusual composition, could warrant a second look. While our moonlet is almost certainly natural, its very existence teaches us what to flag as interesting in databases of exo-objects. The line between natural oddity and potential artifact might blur in the vastness of space, making our local outlier an unexpected guide in the search for extraterrestrial intelligence. Ultimately, this tiny world reminds us that the universe loves exceptions. Every solar system, no matter how orderly it appears, likely harbors its own rebels objects that refuse to follow the script. By embracing the chaos in our backyard, we sharpen our ability to decode it elsewhere. And as telescopes grow more powerful, revealing finer details of distant belts and moonlets, the lessons from this one stubborn object might illuminate corners of the cosmos we've only begun to imagine. While giant telescopes and space agencies dominate headlines, some of the most crucial observations of this rogue moonlet have come from backyard stargazers armed with nothing but passion and modest equipment. In 2022, an amateur astronomer in New Mexico noticed an odd blip in their tracking data, a slight deviation from the moonlet's predicted path that professional observatories had missed. At first, researchers dismissed it as equipment error until 3 more citizen scientists across different continents reported the same anomaly. Suddenly, a pattern emerged. This wasn't noise in the data. The moonlet had hiccuped, and the global network of amateur skywatchers had caught it red-handed. What makes these contributions so vital is their unique vantage point. Large telescopes operate on tight schedules, often prioritizing deep space galaxies or high-profile targets. But amateur astronomers can monitor the asteroid belt relentlessly, logging hundreds of hours of observation that no funded program would justify. Their smaller scopes might lack resolution, but they make up for it in quantity, like 1,000 security cameras capturing different angles of a suspect's movements. Platforms like Zooniverse now aggregate these sightings, letting volunteers tag anomalies that algorithms might overlook. The result, a living map of the moonlet's antics, richer than any single observatory could produce. The collaboration goes beyond spotting deviations. In 2023, a retired engineer in Finland devised a clever hack to measure the Moonlet's rotation using consumer-grade equipment. By timing subtle brightness changes as its irregular shape turned, they calculated a spin rate that contradicted earlier NASA estimates. When professionals rechecked with Hubble, the amateur was proven right. It's a reminder that innovation doesn't always come from billion-dollar labs. Sometimes it's a tinkerer in a garage who spots what others miss. This grassroots effort mirrors historic breakthroughs like William Herschel's discovery of Uranus or Clyde Tombaugh's identification of Pluto, era-defining finds made without professional training. But today's citizen scientists have an edge their predecessors lacked: instant global collaboration. Online forums buzz with real-time updates, where enthusiasts from Tokyo to Cape Town cross-check each other's data. One group even built an AI model trained on amateur observations, predicting the Moonlet's next detour weeks before it happened. The implications stretch far beyond this one mystery. As asteroid mining and planetary defense gain urgency, crowdsourced monitoring could become our early warning system. Imagine thousands of eyes tracking near-Earth objects, their combined data spotting dangerous trajectories long before official surveys. For now, though, their focus remains on our solar system's tiniest troublemaker, a reminder that sometimes the biggest leaps in science start with someone staring at the stars, not for a paycheck, but for the sheer wonder of it. And as long as this Moonlet keeps defying predictions, those watching from their backyards will be the first to sound the alarm. There's something deeply humbling about this Moonlet's defiance, not just for astronomers, but for anyone who's ever looked up at the night sky and wondered how the universe works. In an age where we've mapped the human genome, photographed black holes, and sent probes beyond our solar system, here's a rock the size of a skyscraper reminding us that nature still writes its own rules. It's as if the cosmos is whispering, "You think you've figured me out, try again." This tiny rebel doesn't just challenge our equations, it nudges us toward a profound truth: that mystery isn't a flaw in science, but its very essence. Consider how far we've come since Galileo first turned his telescope toward Jupiter's moons. We've reduced celestial motion to elegant mathematics, predicted eclipses centuries in advance, even landed robots on Mars with pinpoint precision. Yet this Moonlet's chaotic dance exposes the cracks in our certainty. Like quantum physics did a century ago, it reveals that beneath every law we've codified, there may be layers of complexity we've yet to touch. Some philosophers of science argue that anomalies like this aren't roadblocks, they're signposts, pointing toward deeper truths waiting to be uncovered. After all, Neptune was discovered because Uranus's orbit didn't behave as predicted. What if this Moonlet is hinting at an equally revolutionary insight? What makes its defiance especially poignant is how it mirrors the human journey of discovery. For centuries, we saw the solar system as a perfect clockwork, until Kepler's ellipses shattered that illusion. Then Newton gave us gravity's pull, only for Einstein to show space itself could bend. Now, as we stand on the shoulders of those giants, this Moonlet asks, what's next? Its stubborn unpredictability keeps science honest, preventing the complacency that comes with thinking we've solved the puzzle. In that sense, it's not an obstacle, but a gift, a perpetual reminder that wonder shouldn't fade with knowledge, but deepen. Perhaps most beautifully, this cosmic outlier bridges the gap between the known and the unknown. Every time it zigged when our models said it should zag, it didn't just break a calculation, it expanded the boundaries of what we consider possible. That tension between prediction and surprise is where discovery lies. Whether the answer lies in unseen forces, flaws in our models, or something entirely new, one thing's certain: the universe is richer, stranger, and more imaginative than our boldest theories. And as long as mysteries like this moonlet endure, so too will our drive to explore them, not just to find answers, but to savor the questions themselves. The next generation of telescopes might finally crack the moonlet's code, not with bigger lenses, but with smarter eyes. Imagine an observatory that doesn't just stare at the asteroid belt, but anticipates its chaos. The Vera Rubin Observatory, set to begin its decade-long sky survey in 2025, will scan the entire visible sky every few nights with a 3,000-megapixel camera. Unlike Hubble's deep but narrow gaze, this machine will catch fleeting anomalies like our moonlet's sudden course corrections in near real time. It's the difference between snapping a photo of a lightning bolt and filming the whole storm. Combined with adaptive optics that cancel out atmospheric blur, these instruments could trace the moonlet's path with pixel-perfect precision, spotting deviations too subtle for current tech to detect. But raw data isn't enough. That's where artificial intelligence steps in. Traditional orbit models treat gravity as a predictable force, but machine learning thrives on chaos. Teams at Caltech and ESA are training neural networks on the moonlet's historical antics, letting algorithms spot patterns human brains might miss. One prototype AI recently predicted a minor wobble 3 months before telescopes observed it, hinting at hidden gravitational harmonics. Other systems simulate millions of orbital scenarios per second, testing how variables like solar radiation or microscopic debris could reshape the moonlet's path. It's like teaching a computer to play cosmic pinball, where every flipper and bumper represents a force we're still learning to measure. Then there's the frontier of miniaturized space probes. Conventional missions are too bulky and expensive to chase such a small, erratic target, but swarms of smartphone-sized satellites could change the game. NASA's Starlink project aims to deploy CubeSats that fly in formation, using each other's gravity to maneuver precisely. Picture a fleet of these scouts surrounding the moonlet, mapping its magnetic fields, surface composition, and thermal emissions from just miles away. Some designs even include ChipSats, a postage stamp probes that could land on the object itself, measuring vibrations from micrometeorite impacts or residual heat from ancient collisions. Unlike solitary rovers, these networked explorers would create a living 3D model of the moonlet's environment, revealing how external forces warp its trajectory minute by minute. The most radical innovation might be quantum sensing. Lab experiments now show how atomic interferometers, devices that measure gravity using supercooled atoms, can detect mass fluctuations smaller than a grain of sand. Mounted on a future probe, such sensors could map the moonlet's gravitational field in unprecedented detail, spotting hidden density variations or even pockets of exotic matter beneath its surface. Meanwhile, laser-based optical clocks could track its velocity changes with nanometer precision, effectively weighing every gravitational tug it experiences. These technologies sound like sci-fi, but prototypes already exist aboard the International Space Station, quietly revolutionizing how we measure microgravity. What ties these breakthroughs together isn't just better hardware, it's a shift in philosophy. For centuries, astronomy meant passive observation, waiting for the universe to reveal itself. Now we're building tools that actively interrogate cosmic anomalies, treating them not as puzzles to solve, but as teachers with lessons to impart. Whether it's AI uncovering hidden orbital rhythms or CubeSats feeling the push of phantom forces, each innovation brings us closer to answering the moonlet's riddle. And in doing so, they're rewriting the playbook for how we explore not just asteroids, but every uncharted corner of the cosmos. The hunt to decode this cosmic rebel has become a global obsession, uniting space agencies in a way reminiscent of the International Space Station's collaborative spirit. NASA Jet Propulsion Laboratory shares radar data with the European Space Agency, while Japan's Hayabusa team contributes precision trajectory models honed during their asteroid sample return missions. Even emerging space powers like India and the United Arab Emirates have redirected telescopes to monitor the Moonlet's antics, their normally competitive programs pausing to pool resources. This isn't just about sharing notes, it's a coordinated assault on one of the solar system's most stubborn mysteries, with researchers working across time zones to piece together observations like a planetary-scale detective squad. What makes this cooperation remarkable isn't just its scale, but its urgency. Unlike the decades-long ISS partnership, this Moonlet task force formed almost overnight after its orbital anomalies became undeniable. Weekly virtual summits see scientists from 15 nations debating fresh data, their home institutions' rivalries set aside in favor of collective breakthroughs. The European Space Agency's Gaia star mapping mission, initially designed to chart distant galaxies, has repurposed some instruments to track the Moonlet's subtle positional shifts. Meanwhile, Russia's dormant radio telescopes in Siberia, once Cold War relics, now hum back to life, their massive dishes fine-tuned to catch faint reflections from the object's metallic surface. Collaboration extends beyond hardware. China's Chang lunar mission team has adapted their navigation algorithms to model chaotic orbits, sharing code that helped explain why the Moonlet's 2021 trajectory veered unexpectedly. Brazil's atmospheric scientists contributed turbulence models normally used to predict Amazonian weather, revealing how solar wind fluctuations might amplify the object's tumbling. Even amateur astronomy networks in Africa and Southeast Asia, often overlooked in major projects, provide crucial longitudinal data when professional telescopes lose sight of the Moonlet behind the Sun. This decentralized approach mirrors how epidemiologists tracked COVID variants, except here, the target isn't a virus but a celestial body rewriting physics. Historical parallels abound. The same spirit that drove 19th century astronomers to coordinate observations of Venus's transit across the Sun now fuels this Moonlet chase. Back then, nations raced to distant corners of the globe with telescopes. Today, they link satellites and supercomputers across orbital planes. But there's a key difference. Where past collaborations sought to confirm established theories, this one thrives on embracing the unknown. Every time the Moonlet defies prediction, it doesn't frustrate these researchers, it electrifies them. Because in that defiance lies the thrill of discovery, the chance that their collective effort might reveal something fundamental about how gravity, chaos, and time intertwine in the cosmic dance. Perhaps most unexpectedly, the partnership has birthed new diplomatic channels. When political tensions froze joint Mars missions between some nations, their scientists continued collaborating quietly on Moonlet research through neutral academic hubs. The object's sheer scientific value has become a rare unifying force, proving that curiosity knows no borders. Private companies are joining two SpaceX-adjusted Starlink satellite orbits to avoid interference with crucial observation windows, while asteroid mining startups share radar bandwidth in exchange for data that could help navigate treacherous belts. As this international brain trust grows, so does their ambition. Plans are underway for a dedicated microsatellite swarm with components built across 4 continents to form a distributed sensor network around the Moonlet. It's a testament to how one stubborn space rock has done what decades of diplomacy sometimes couldn't: turn competitors into collaborators, all chasing the glow of a shared mystery against the infinite black. And in that shared pursuit, they're rediscovering the oldest truth in science, that the universe's greatest puzzles were never meant to be solved alone. This cosmic rebel isn't just confounding scientists, it's reshaping classrooms. From middle school physics labs to Ivy League lecture halls, the Moonlet's Defiance has become a masterclass in how real science unfolds. Forget tidy textbook diagrams of perfect ellipses. Here's a celestial object that treats orbital mechanics like a choose-your-own-adventure novel. Professors now project its erratic path alongside Newton's pristine laws, not to contradict them, but to show how reality often wears the cracks between theory and discovery. One MIT professor famously begins her astrophysics course by asking students to predict the moonlet's next move using classical equations. When every calculation fails, as they always do, the lesson hits home. Science isn't about memorizing answers, but learning to ask better questions. The moonlet's educational power lies in its imperfections. While most astronomy demos use polished examples like Pluto's orderly moons, this misfit offers something far more valuable: the messiness of authentic research. High school teachers report students lighting up when tasked with brainstorming explanations for its chaos. Could solar radiation be warping its metal-rich surface? Might microscopic craters act like thrusters when sunlight hits them at certain angles? These aren't canned exercises, they're miniature versions of the debates happening in Nature journal articles. At the University of Tokyo, a student team even built a scale model in a zero-gravity simulator, sprinkling iron filings onto a spinning core to test how metallic composition affects tumble rates. Their unexpected discovery: certain asymmetric shapes amplify tiny forces dramatically, a clue that might explain why the real moonlet veers so wildly. Beyond physics, the object story teaches a meta-lesson about scientific humility. Textbooks often present discoveries as linear triumphs, glossing over centuries of dead ends and stubborn anomalies. But here's a case study in real time where the smartest minds keep hitting walls. NASA Jet Propulsion Laboratory openly shares its failed trajectory models with universities, turning each computational flop into a learning opportunity. One Berkeley grad student's viral blog post put it perfectly: "Watching professionals wrestle with this moonlet is like seeing your math teacher work through a problem they haven't solved yet." It humanizes the entire scientific process. Perhaps most inspiring is how the mystery bridges disciplines. Art students sketch speculative renderings of its metallic surface, while creative writing classes craft stories about its origins. A viral TikTok trend even has chemistry majors analyzing spectral data for fun, identifying possible alloy combinations that could explain its unusual reflectivity. This cross-pollination mirrors how groundbreaking science actually happens, not in isolated silos, but where fields collide. The moonlet doesn't just defy gravity, it defies academic boundaries, proving that the best education happens when curiosity isn't confined by subject lines. And that may be its greatest legacy. Long after astronomers pin down its secrets, if they ever do, this cosmic troublemaker will endure as a reminder that science isn't a static set of facts, but a living conversation with the universe. Every time a student gazes at its latest erratic loop and thinks, "Wait, that shouldn't happen," they're stepping into the same shoes as Galileo, Kepler, and Einstein. Not to recite what's known, but to explore what remains gloriously, tantalizingly unknown. Hollywood wasted no time turning this cosmic rebel into a silver screen star. Within months of its discovery, a major studio greenlit a thriller where the moonlet's erratic orbit triggers a chain reaction threatening Earth, complete with dramatic shots of its metallic surface glinting ominously against the void. What makes it such a gift for storytellers isn't just its real-life defiance of physics, but its tantalizing ambiguity. Is it a natural oddity or something more? A sci-fi anthology series last season explored both angles in parallel episodes, one where scientists uncover its artificial origins as an ancient alien probe, another where it's revealed to be a fragment of a collapsed higher dimension. The show's creator admitted in interviews they didn't need to invent much. The Moonlet's actual scientific bafflement did most of the heavy lifting. Beyond blockbusters, the object has become a muse for speculative fiction's literary elite. A Hugo-winning novella reimagined it as the last remnant of a parallel universe's asteroid belt, drifting into ours through a quantum tear. The story's protagonist, a disillusioned astrophysicist, finds solace in tracking its chaotic path, a metaphor for life's unpredictability that resonated deeply with readers. Even video games have gotten in on the action, with a popular space simulator adding the Moonlet as a dynamic navigational hazard. Players who attempt to land on its surface trigger hidden storylines about rogue AI or precursor civilizations, rewarding those bold enough to chase the unknown. The most fascinating adaptations aren't the futuristic ones, but the period pieces. A critically acclaimed radio drama set in the 1960s follows Soviet and American scientists racing to interpret the Moonlet's then unexplained orbital quirks, their Cold War tensions mirrored by its refusal to align with either side's models. By grounding the mystery in historical realism, the show highlights how scientific discovery often blooms at the intersection of competition and curiosity. Meanwhile, indie filmmakers have taken an experimental approach. One Sundance short film depicts the Moonlet entirely through distorted reflections in astronomers' eyepieces, its true nature always just out of focus. What these creative interpretations share is a recognition of the Moonlet's narrative superpower. It embodies the thrill of the unsolved. Unlike fictional mysteries where answers eventually come, this one remains stubbornly open-ended in reality, letting each storyteller project their own meaning onto its metallic surface. For some, it's a cautionary tale about humanity's hubris; for others, a symbol of cosmic wonder. The object's refusal to be categorized makes it the perfect Rorschach test for our collective imagination, a blank canvas orbiting silently between Mars and Jupiter, waiting for the next artist or scientist to try decoding its secrets. And in that tension between fact and fiction, something magical happens. The Moonlet stops being just a space rock and becomes a mirror reflecting our deepest questions about the universe and our place within it. The idea of nudging this cosmic rebel onto a more predictable path for study might sound like a no-brainer after all. What's the harm in giving a tiny space rock a gentle push? But the moment we consider intervening, we step onto ethically fraught ground. Space isn't just a vacuum waiting for our experiments. It's an ancient, interconnected system where every object, no matter how small, plays a role in a delicate gravitational ballet. Take the Moonlet's current orbit. Chaotic as it is, its path might be subtly stabilizing other asteroids we can't yet perceive. If we alter its trajectory, could we unintentionally send a neighboring rock spiraling toward Mars, or worse, Earth? History offers sobering parallels. When engineers diverted rivers to build dams, they often triggered unforeseen ecological cascades. The cosmos operates on an infinitely grander scale, where unintended consequences could span millennia. Then there's the philosophical question: do we have the right to interfere? Celestial bodies have existed for billions of years untouched by human hands. Some argue that manipulating them, even for science, crosses a line akin to vandalizing a natural wonder. Indigenous cultures, for instance, view certain astronomical phenomena as sacred, woven into creation stories and calendars. While this Moonlet may not hold cultural significance, the precedent we set by altering it could ripple outward, normalizing the idea that space is ours to rearrange at will. Contrast this with the leave no trace ethos guiding modern wilderness preservation. If we wouldn't carve our initials into the Grand Canyon, why scribble equations across the asteroid belt? Yet the counterarguments are compelling. Humanity's survival may one day hinge on understanding chaotic orbits like this one. Near-Earth asteroids pose real threats, and mastering the mechanics of erratic motion could be the key to deflecting them. Proponents of intervention point to NASA's DART mission, which successfully nudged an asteroid's Moonlet in 2022, a test run for planetary defense. If we can steer a harmless rock today, we might save lives tomorrow. The Moonlet's Defiance makes it the perfect training ground, a controlled experiment in cosmic billiards where the stakes are low but the lessons profound. The debate grows murkier when we consider ownership. International space treaties forbid nations from claiming celestial bodies, but say little about modifying them. If one country or corporation unilaterally decides to alter the Moonlet's orbit, who holds them accountable? The asteroid belt is already a potential gold mine for rare metals, and precedents set here could fuel a free-for-all. Imagine a future where mining companies tweak asteroid orbits to bring resources closer to Earth, inadvertently destabilizing the belt. The Moonlet might be small, but the ethical framework we build around it could shape humanity's conduct in space for centuries. Perhaps the answer lies in a middle path, studying the Moonlet without brute force intervention. Advanced sensors could map its gravitational field in unprecedented detail, while passive observation campaigns might reveal hidden forces influencing its path. Some scientists propose tagging it with reflective markers or deploying swarms of microprobes to orbit at a safe distance, gathering data without direct interference. This approach honors both curiosity and caution, treating the Moonlet less as a lab specimen and more as a teacher whose lessons unfold on its own terms. After all, its greatest value might lie not in the answers it surrenders, but in the questions it compels us to ask about our place in the cosmos, our responsibilities as explorers, and the humility required to navigate a universe that still, stubbornly, refuses to follow our rules. The Moonlet's metallic heart doesn't just confound scientists, it sparks dreams of cosmic fortune. Asteroid mining has long been the stuff of sci-fi, promising untapped veins of platinum, gold, and rare earth metals floating in the void. But this particular rebel presents a tantalizing paradox. Its composition suggests a treasure trove, while its chaotic orbit makes it the ultimate moving target. Picture a vault of precious metals tumbling through space at unpredictable speeds, daring prospectors to chase it. The economic potential is staggering. Just a single metal-rich asteroid could contain more platinum than has ever been mined on Earth. Yet the Moonlet's refusal to follow the rules turns what should be a straightforward extraction equation into a high-stakes gamble. Current mining concepts rely on stable orbits. Companies like Planetary Resources and Deep Space Industries have spent years designing robotic miners to latch onto predictable asteroids, processing ore on site, or nudging entire rocks into Earth-friendly trajectories. But none of their blueprints account for an object that changes course like a rogue pinball. Landing equipment on the Moonlet would be like trying to dock with a spinning carnival ride. One miscalculation, and your billion-dollar harvester becomes space junk. Even capturing it in a net of gravitational tethers, a proposed method for stabilizing small asteroids, seems futile when its path defies all models. The very unpredictability that makes it scientifically fascinating renders it nearly impossible to exploit with today's technology. Yet impossibility has never stopped human ambition. Some engineers are already brainstorming workarounds. One radical proposal involves deploying a swarm of nanoprobes that could match the Moonlet's erratic movements, anchoring to its surface like magnetic ticks to extract trace metals particle by particle. Another envisions a lasso and tether system, a spacecraft that wouldn't chase the Moonlet, but wait in its projected orbital zone, casting a wide net of graphene cables to snag it during a close pass. These ideas border on speculative fiction, but they highlight a critical truth. Where there's material value, innovation follows. The same drive that propelled gold rushes and deep-sea drilling might one day crack the code of chaotic asteroid mining. The financial calculus is equally fraught. Traditional cost-benefit analyses assume stable operations over decades, but mining this Moonlet would require constant recalibration, burning fuel and time with no guarantee of payoff. Insurance underwriters balk at the liability. Imagine a wayward mining probe accidentally deflecting the Moonlet into a collision course with other belt resources. Yet the metals locked inside could rewrite global markets. A single shipment of asteroid platinum might crash terrestrial prices, destabilizing mining economies from South Africa to Siberia. Some economists argue this volatility itself could become an asset, with futures traders speculating on extraction windows between the Moonlet's orbital tantrums. Beyond pure economics, the Moonlet forces us to confront bigger questions about resource ethics in space. Unlike Earth's finite deposits, the asteroid belt's riches are theoretically limitless, but only if we can access them sustainably. Hauling this rebel's metals home might jumpstart orbital manufacturing or fuel deep space missions, reducing our reliance on environmentally destructive terrestrial mining. Alternatively, it could trigger a free-for-all, with corporations and nations scrambling to claim chaotic asteroids before regulations catch up. The Moonlet's Defiance isn't just a navigational headache, it's a litmus test for whether humanity can harvest the cosmos without repeating the mistakes we've made on our own planet. Perhaps the most intriguing possibility isn't mining the Moonlet at all, but learning from it. Its metallic structure could hold clues to forming metal-rich asteroids in more stable orbits, ones that might be easier to exploit. By decoding why this fragment behaves so wildly, we might uncover geological processes that concentrate precious metals elsewhere in the belt. In that sense, the Moonlet's greatest economic value might lie not in what we can take from it, but in the knowledge it offers about where else to look. After all, the best treasure maps aren't the ones that lead to a single chest, but those that reveal the patterns hiding 1,000 more. The Moonlet's hypersensitivity to the faintest cosmic nudges mirrors a phenomenon we know all too well on Earth, the butterfly effect in climate systems. Just as a degree's shift in ocean temperature can amplify into hurricanes halfway across the globe, this tiny asteroid's orbit spirals into chaos from forces that wouldn't budge a larger world. Researchers studying both fields are uncovering eerie parallels: how minute variables, once dismissed as noise, can tilt entire systems toward unpredictability. Take Earth's jet streams, those high-altitude air currents that steer weather patterns. A slight warming in the Arctic, barely noticeable at first, can buckle these atmospheric rivers, triggering heat waves in Europe and floods in Asia. The Moonlet operates under similar rules, where a pebble-sized asteroid's gravity or a whisper of solar wind might steer it onto a radically new path centuries later. What makes these connections more than poetic is the math behind them. Climate scientists and astrophysicists increasingly borrow each other's tools to model chaos. The same equations that predict how melting ice sheets might disrupt ocean currents also simulate how our Moonlet's orbit fractures under Jupiter's gravitational harmonics. Both systems exist in what mathematicians call metastable states, appearing calm until a critical threshold tips them into turmoil. For Earth, that might mean collapsing ice shelves. For the Moonlet, a sudden leap into resonance with Mars. The key insight: stability is often an illusion, whether you're tracking CO2 levels or celestial mechanics. There's practical value in this crossover. NASA climatologists, accustomed to parsing chaotic atmospheric data, have helped asteroid modelers clean up noisy observations of the Moonlet's path. Conversely, algorithms first developed to trace interstellar dust trails now improve hurricane prediction models. The most promising collaboration centers on early warning systems. Just as climatologists monitor subtle shifts in Antarctic ice for signs of impending collapse, astronomers now watch for microscopic deviations in the Moonlet's spin, hints that it's gearing up for another orbital pirouette. These parallels suggest a universal truth. Whether you're studying planets or climate, the tiniest signals often carry the most urgent messages. Yet the Moonlet offers something climate models lack: a controlled experiment. Earth's climate drowns in variables: deforestation, pollution, ocean cycles, all tangled together. But space is a cleaner lab. The forces acting on our rebellious rock, however complex, are fewer and simpler to isolate. By seeing how it responds to calculated nudges like changes in solar radiation or nearby asteroids, we might uncover patterns applicable to Earth's own delicate balances. Imagine if understanding why the Moonlet veers left when pushed right could help predict how the Gulf Stream might react to melting Greenland ice. That's the transformative potential of this cosmic climate dialogue. The lesson isn't just scientific, it's philosophical. Both the Moonlet and Earth's climate remind us that fragility and resilience are two sides of the same coin. A system exquisitely sensitive to small changes isn't necessarily weak. Sometimes that sensitivity is what allows adaptation. Coral reefs bleach under slight temperature shifts but also regenerate when given respite. The Moonlet's wild orbit might look like dysfunction, but it's also evidence of a system vibrant with possibility, capable of dancing where others would only fall. In the end, whether we're gazing at climate graphs or asteroid tracks, we're really seeing the same story: a universe where little things matter most, and where understanding the smallest wobbles might help us navigate the biggest storms. A century from now, astronomers might look back at our confusion over this Moonlet and smile, or they could still be scratching their heads, watching its latest unpredictable loop with the same awe we feel today. The trajectory of scientific discovery rarely runs in straight lines, and this cosmic rebel embodies that truth perfectly. On one hand, advances in quantum gravity theory, ultra-precise spaceborne interferometers, and AI-powered chaos modeling could finally crack its secrets, revealing the hidden forces behind its dance. Imagine a future where schoolchildren learn about Moonlet mechanics as routinely as Kepler's laws, its once baffling motions now distilled into elegant equations. Space agencies might even use it as a testing ground for manipulating chaotic orbits, harnessing its unpredictability to practice steering hazardous asteroids away from Earth. Yet history whispers a cautionary tale. Some cosmic puzzles stubbornly resist resolution, like the lingering mystery of Uranus's off-kilter axis or the true nature of dark matter. Our Moonlet could follow that path, its secrets deepening as our tools improve. Future astronomers armed with planet-sized radio telescope arrays might discover its chaos stems from phenomena we can't yet imagine. Microscopic black holes orbiting its core, quantum gravitational fluctuations, or even relics from before the Big Bang frozen in its metallic heart. Each answered question could spawn 10 more, proving that some cosmic riddles exist not to be solved, but to pull us deeper into the universe's wonders. What makes this uncertainty thrilling is how it mirrors science's grand tradition. Every generation believes they're on the verge of final answers, only for the next to uncover vaster unknowns. Victorian scientists thought Newton had penned gravity's last chapter until Einstein showed it was just the preface. Today's researchers might be in the same position with this moonlet, standing at the edge of a revelation that will rewrite celestial mechanics yet again. Or they might be the lucky ones witnessing the early stages of a mystery that will endure for millennia, a perpetual reminder that the universe always keeps a few cards close to its chest. Perhaps the Moonlet's ultimate lesson isn't about orbits at all, but about how we confront the unknown. In a world increasingly obsessed with instant answers, its persistent defiance of prediction teaches patience, the value of sitting with questions rather than rushing to conclusions. Future scientists may honor it not for the secrets it surrendered, but for how it trained generations to embrace uncertainty. After all, the night sky's greatest gift isn't the comfort of perfect knowledge, but the exhilarating whisper that there's always more to discover. Whether this tiny world becomes a solved equation or an eternal enigma, its true legacy will be keeping that flame of curiosity alive. The tiny moonlet's defiance of orbital predictions is more than a scientific curiosity. It's a beacon of the unknown, a flickering signal in the cosmic noise that reminds us how much we have yet to learn. Think about it, in an era where we've mapped the human genome and photographed the edges of black holes, a chunk of metal and rock no bigger than a skyscraper still leaves the brightest mind stumped. That's not a failure of science, it's a triumph, because every time this moonlet veers off script, it's nudging us toward deeper questions, forcing us to re-examine the very laws we thought governed the heavens. Look at how far its influence has already spread. What started as a blip in telescope data has united space agencies, inspired citizen scientists, and even sparked Hollywood blockbusters. It's become a shared obsession, bridging languages and borders with the universal language of curiosity. The same object that flummoxed supercomputers has also, improbably, brought people together, proving that the mysteries of the cosmos can still stir something primal in us, something that transcends algorithms and equations. There's poetry in that. A rock hurtling through space, oblivious to its own notoriety, has become a mirror reflecting our collective wonder. But the moonlet's greatest gift might be the humility it teaches. In a world where we're conditioned to expect instant answers, its stubborn refusal to conform is a masterclass in patience. It whispers that some truths unfold on their own schedule, indifferent to our deadlines or desire for neat resolutions. And that's okay, because the joy isn't just in solving puzzles. It's in the chase, the collaboration, the late-night debates over coffee and star charts. Whether we crack its code next year or a century from now, the journey itself has already reshaped how we see our place in the universe, so keep looking up. The next time you gaze at the night sky, remember, out there in the asteroid belt, a tiny rebel is still dancing to its own rhythm, daring us to keep up. Maybe the solution lies in an equation we haven't written yet, or a force we've yet to discover. Or maybe, just maybe, you'll be the one to connect the dots. After all, the most groundbreaking discoveries often start with someone asking, "Wait, why does it do that?" Drop your wildest theories in the comments below. Hit like if you love cosmic mysteries, and subscribe to join us as we chase the next great enigma among the stars. The universe is full of them, and that's what makes it so